Great, thanks very much for coming to this talk, Redefining Supercomputing on AWS. So we want to talk about supercomputing, but what exactly is it and why does it matter? I'd like to start by maybe telling a little bit of a story about how I was first introduced to supercomputing and how it's helping to better understand the world around us. So I'm an engineer by trade. I did it because I dreamt of designing Formula One cars or designing rockets that could take us to another planet. But what's really interesting is that actually the one thing that unites this, or even something like the Mars lander, is that if you want to design better vehicles in this case, whether it's a car, a rocket, or a spacecraft landing on another planet, you have to understand how it operates with the world around. You have to understand the physics. And all of them are interacting with the atmosphere around. Okay, on Earth it has a certain characteristic, on Mars it's different. But if you're designing a car, it moves through the air. You want to understand how it interacts with the air. As the rocket takes off, you have to understand that. And of course, if you're landing on a planet. Now, you can actually do this in some ways using physical tests. So if I want to design a better Formula One car, I could actually build one and take it onto a track. But that actually ends up being quite expensive because you have to physically make this thing and take it around. And if you just want to optimize it, it's probably not the quickest way to be doing that. But it's possible. You could also use things like wind tunnels that are essentially a huge warehouse with a big fan that blows air over this thing to do more of an experiment. So it's not the real world, but it's close to it. But again, you've got to make this vehicle, you've got to take it there. So from a design point of view, it's a little bit slower, but you could do it in theory. When you get to something like a rocket, then actually it becomes even more difficult. A really interesting use case is for anybody who's actually seen the shuttle or the rockets take off. They actually have a pool of water underneath. And interestingly, one reason for that is because of the temperatures that the plume puts onto the launcher. But the other thing is actually as they start to ignite, there are pressure waves that get generated essentially from the noise, and that could potentially damage or destroy the actual launch infrastructure. So they have water there to dampen out those waves. But how much water do you need? It's actually very hard to do a physical test because it's so expensive and difficult to do these rocket launches. So you'd ideally want a way of simulating that. And if you go to something like the Mars lander on another planet, it's an order of magnitude more complex to do those sort of testing. And of course, you've got to come up with a way of replicating the gravity and the atmosphere. So there is a valid reason to maybe try to simulate something rather than doing an actual physical test. And so we're lucky that in this particular area, we're talking about fluid and fluid flow. Around 200 years ago, these two scientists actually derived these equations, these Navier-Stokes equations, that if you can solve them, then you can actually understand what's going on with the flow in a purely analytical way. But the problem is these are extremely complex to solve, nonlinear equations. So actually you can't do it. You have to use some sort of numerical approximation to do it. Now, what it turns out is that this approach, which is more commonly referred to as computational fluid dynamics, you take the object. So in this picture, it's an aircraft, but it could be this room here. There's probably been computational fluid dynamics simulations to assess the air conditioning in the room or the fire safety protocols. But if it's this aircraft here, what you do is you actually split the domain up and you solve these Navier-Stokes equations over these elements. But you need a lot of these elements or cells because of the nature of airflow or fluid flow. They operate at the smallest possible scales, millimeters or tenths of millimeters. But the plane is huge. So you've got this wide range of length scales, which basically means you end up having hundreds of millions or even billions of these cells. Now, for people with a maths background or computer science, you may see this as essentially just very large matrices that contain these values. So you end up having a humongous amounts of storage and computation required. But there's another thing as well which makes this a complex thing, and that's that the air itself, or the fluid, is inherently unsteady. So not only do you have to solve these set of equations over all these potentially billions of cells, but you have to do that at very small time increments. You have to do it not only to capture the smallest time as these fluid particles move, but you need to do it sufficiently long what would happen in reality. So it takes time for an air to move over this aircraft. So you have to simulate seconds. What this basically means is that not only do you have to solve these equations over billions of cells, you have to do potentially hundreds of thousands of them. So all of this combines to mean you need huge computational resources. And in theory, you could try to somehow magically create a really powerful just single machine, but you would very quickly run into the limits of memory and just general computer architecture, to the point the classic analogy would be, if I was running this simulation on my laptop, it would actually take years to run. I mean, it wouldn't actually run because there wouldn't be enough memory, but if we assume we did, it would take years. So, of course, what we do is we split the problem up. This is essentially the beginnings of what we're starting to talk about with supercomputing or high-performance computing. The analogy is that we say, if we have this domain of these billions of cells, we split it up and we say that one processor will take this clump of cells, and another processor will take the other one, and so forth, until you split this up into potentially thousands of processors. But what makes it computationally challenging is that because of the nature of these algorithms, they have to communicate with each other, both to the processor next to it to transfer information, but quite often globally to all the processors. And this puts high demands on the way that this computer system is organized, particularly on the network. Now, what's interesting with this is there is a limit. This doesn't carry on forever. I can't keep splitting up this problem onto more and more machines and hope that it will keep reducing the time from years to hours. Actually, what ends up happening is you reach a limit where the scaling becomes nonlinear. What this essentially means is, at some point, you're essentially getting a speed up for free. You're not paying any more. You're doubling the number of computers you use, but you're halving the time it takes. Fantastic. But at some point, the time that it takes to do this communication between all these processes starts to become a noticeable part. So much so that when you start adding more computers, you don't actually get a perfect speed up. And in some ways, very simplifying things, one of the key things that the HPC and supercomputing community has tried to do is move that point further to the right, so that you can keep trying to get that speed up to make the simulations run quickly without paying the penalty for the communication. So what I've tried to do there is just give you an example of the actual physics problem, the reason that we need computing. But actually, I've skipped over a huge area of what really is supercomputing and where did it start. So for that, I'd like to invite Heidi to talk about really where supercomputing came from and where it's going to go next. So over to you, Heidi.
So I want to talk a little bit about where supercomputers came from and where we are today with them. I had the privilege through most of my career to be able to work on supercomputing systems, some of the largest and fastest in the world. And what I learned when I came out of school is that I really liked to make things go fast, and I liked to figure out ways to solve things that may seem like they have no solution. So one of the things that's been very important to me throughout my career is to be able to give tools to scientists and engineers so that they can solve problems that they've never been able to solve before. So where did this all start? So you got an introduction from Neil about the complexity of the compute that is needed to solve some of these problems, like to study airflow around different objects like airplanes and cars. This sort of thing has been going on for a long time. Supercomputers have been built since the mid-1960s. The very first one was built by Control Data Corporation and was designed by someone named Seymour Cray. He's been known throughout history to have designed a lot of supercomputing systems. So my first exposure was a Cray 2, and I was very excited about running on that particular system. What these systems have is the ability to run at very large scale and to solve very complex problems, to do numerical calculations that can't be done on smaller systems. They're designed and architected so that they can work together, the components work together to be able to run the type of workload that Neil talked about, where you split a problem into multiple pieces so that you have separate workers that can share the load, share the burden, to solve that problem more quickly. So the first thing is, how do we measure the capability of these supercomputers? Has anyone heard of the top 500 list? Okay, the top 500 list is a list that is, it is collected 2 times a year in June and in November. People submit to that list and they submit the numerical computing capability of their system, of their supercomputer. And in the 1960s, that one of those first supercomputers that was designed was one that was able to calculate a few megaflops. So what is a flop? A floating point operation per second. It's basically a floating point calculation that you can do, whether it's an add, a multiply, that you can do per second. So a mega is 1,000,000. So in 1960s, you could do 1,000,000 floating point operations per second. That has progressed over the years now. So we've gone from mega and moved to giga and moved to tera, peta. In the 2009, 2010 timeframe, we had petaflops. And this year in June of 2022, the submission, the first and fastest system that was on the list was a system that had a little over an exaflop. And we'll talk a little bit more about that. So flops is how we kind of rate these systems in capability, and this has been going on for a very long time. I do want to talk a little bit about the characteristics. What do people expect from these types of systems? Kind of foreshadowing on how this connects to AWS. So first of all, people run, multiple people typically share these systems. They use a queuing system to each get a slice of this supercomputer to be able to work on. Once they get their slice, those nodes, which would be individual servers potentially, would be all theirs to use for that particular run or that particular job. If they were going to communicate on multiple nodes, which most people do on supercomputers, that network, once you get onto the network, is shared across all those users. And so people work very hard to design networks so that they can be performant to handle workloads, and that they can also be able to deliver data between these individual nodes very quickly. The nodes are expected to perform very fast. Typically, it's leading technology processors that are in these supercomputers. So these nodes are fast. They have cores, maybe high frequency, different types of memory. So people, when they're architecting these supercomputers, really work to create a balanced system so that things can work in harmony. The compute, the network, and the storage can all work in harmony. So a particular user on this system wants to extract the maximum performance that they can. So they're trying to get every little cycle out of that individual node, out of that collection of nodes, out of the network. So they have, as I said, the queuing system. They actually code using parallelism. So basically, as Neil said, they split the problem up into many problems. In addition to just splitting it, they have different levels of parallelism on the systems. Vectors is a form of parallelism. A vector allows you, on different processors like Intel and AMD, a vector allows you to perform more work in an operation than you can with a scalar. So every little tiny piece in the architecture is trying to figure out how to make things go faster. So where are we today? with supercomputing technology. So as I said, in June, we announced the top 500 list for this year, did a little over an exaflop. It was a system that was stood up at Oak Ridge National Laboratory here in the United States, and it performed a little bit over an exaflop using more than 8 million cores. It is a system that consists of both CPUs and GPUs. The GPUs can be used for both compute, and they can be used for things like machine learning and AI. So this particular system, if you want to get a feel for what an exaflop is, if you were to take 7.7 billion people around the planet and give them calculation to do, ask them to calculate every second. So perform a calculation every second. So 7.7 billion people performing a calculation every second. It would take 6 years for those 7.7 people to do the same amount of work that that supercomputer did in 1 second. So that's the capability of this computer technology. So not everybody needs the entire supercomputer, but actually we do have codes that run, an application can use the entire system of a large number of cores, a large number of GPUs to be able to perform their calculations and solve problems. Other users may need smaller systems, smaller carvings out of that supercomputer, and so that's why it typically is a shared system. They've been designed to be general purpose systems up until now because people want to understand, they don't know the next problem that's coming, they want to be able to understand and make sure that the system that they're spending a lot of money on can actually handle the type of workloads. So now, giving you a little bit of history of supercomputers, where we are today, let's talk about what this means and how is AWS connected to that. So the first thing that we're seeing here is that there's a convergence between traditional HPC on-prem systems and cloud. So traditional HPC, we've talked about that. We've talked about the tightly coupled, split the problem up, but everything needs to be close and working together in harmony so that you can get your job done more quickly. We also have AI and ML. So cloud has been doing very well with giving resources and providing capability to perform machine learning and AI. Model training, inference, and those different components we're seeing being used now with traditional HPC. So if you have a simulation, as Neil talked about, where you're looking at airflow on an airplane over maybe an airplane wing, you also now can use ML to drive that simulation. So that simulation can do more than it could before, maybe finer resolution or higher physics fidelity, and it can maybe be done quicker. ML is using HPC simulation and modeling to verify models that have been trained. So the two are kind of working and converging towards each other. So the cloud type of capability that we've been seeing with virtualization and we've been seeing with containerization has now been moving towards more performant components, and the on-prem systems, the supercomputers, the traditional supercomputers, are looking at more complex workflows that include ensembles or that include integrating machine learning, for example. One of the things that we want to make sure that we do at AWS as we design HPC software and HPC services is to make sure that we look for how to make it easier to use for our users. Our customers are our number one priority, and we want to make sure that the pain points or the friction that they see is heard and understood so that we can resolve it. We want to make sure that we can migrate codes easily so that and by doing that, one of the things we can do is create a flexible, familiar environment for our users who typically maybe run on-prem. Maybe you have a favorite language you use, or a favorite compiler you use, or a favorite code that you run. Being able to help with that transition to make it look more familiar is important to us. And then obviously, one of the big things of the cloud is the elasticity and the choice. And that's where the thing comes in that's different from supercomputers. So the first thing is, let's talk about the building blocks, and then we'll talk about how they're all put together. The building blocks that you have for HPC are a suite of compute instances, and these vary depending on the type of workload that you need. Whether you need a lot of cores with high frequency, or you need a large amount of memory per core, maybe you need some local disk, whatever you need, we have a lot of variety of solutions, and we'll talk about some specific instances that have been announced this week and earlier that we use specifically for HPC and why. The middle column has some performance capability that we'll also talk about in a minute here, but I also want to mention that on supercomputers today, one of the things that the workloads typically need is what's called a shared file system. So if you want to perform if you broke up your work across a lot of different servers or a lot of different nodes, and you want to write your results that need to be correlated or somehow stored or read back in, maybe your initial input you need access. All these nodes need access. You want to use a shared file system. You want to use an efficient, fast shared file system. So a lot of supercomputers use what's called a Lustre file system, shared parallel file system, and we have that capability. So one of the things that's different that we have from a general purpose supercomputer is we have the ability to allow our customers to compose infrastructure for their workload or their application. So instead of having an application and you sit on a supercomputer that has been designed so that it runs well, but you have to optimize and tune your application for that infrastructure, a composable infrastructure gives you the option to say, hey, I want to design that infrastructure to meet my workload needs. And that choice and that flexibility is something that AWS has offered to be able to give the meaning of general purpose a little bit of a different twist. So let's talk about those two performant things in the column of the previous slide. The first thing is the AWS Nitro system. One of the things that you get with cloud is you have virtualization. Virtualization is there to protect the hardware, and it's there to protect the BIOS, and it virtualizes the CPU, storage, and network. It also does perform some monitoring capability, management capability. So what AWS has done is, as you see, those types of tasks could potentially take away from computing resources for the end user. So we've offloaded that with hardware and software. We've offloaded that capability. In the upper right of this particular slide, what you'll see is we have a code that was run across 16 instances or 16 nodes. The top line at the red line across the top horizontally is a version of that particular instance that does not use virtualization. We call it bare metal. And then the bars, the orange bars, are for those codes that are running in our virtualized environment with the hypervisor. And so what you'll see is for those OpenFOAM, GROMACS, WRF, and HPL codes, the performance is over 99% of this, the same as bare metal. And so there is very little, if no noticeable, difference between the bare metal and the virtual with our hypervisor. What this does is, remember earlier I said users want to be able to use all the resources available to them on a supercomputer. So this is one of the things that we do very well with our instances, in that we have offloaded some of this overhead here. The next thing that we want to talk about is the network. So a performant network is also important. As you split up this work across instances or across nodes, you want to make sure that you can move data between them very quickly. The way that we do this is we have taken our Ethernet network, our backbone network, and we've created an elastic fabric adapter on top of it that allows us to deliver high bandwidth and low latency for the applications. Instead of the traditional TCP stack, which a lot of people can use if you don't need the high performance network, we offer the option for high performance network. And we'll talk about that with these instances and what sort of performance you see. But as it was mentioned earlier this week in the keynotes, we now are supporting up to 8 gigabits per second for bandwidth for this particular, for our EFA. So what about instances? So we have a diverse set of workloads with supercomputers. People that are in HPC tend to not all run the same thing. Some people need a lot of computation, fast computation. Some people need a lot of memory. Some people need local disk. So for example, if you were performing a bunch of temporary I/O that you were then again going to read, you may want to have this on local disk so you're not going all the way to some remote storage, even if it's fast. Having something really close by is typically faster. You may have something where you need to maybe have a graph you want to store in memory, or you want to be able to perform all the work in memory, and you don't want to have to split that particular piece of your work across different nodes. You need it to fit in memory. So we've developed a couple of tracks of instances now for HPC users. So we have the compute-intensive instances, and we have the compute and network-intensive instance that was just recently announced. This is based on our Graviton line. We'll talk more about each one in a minute here, but the other one is our data and memory-intensive instance. So what this gives our users now is choice. So instead of a single general purpose system that decides how much memory you need for each core and that decides how much local disk, if any, to have, now you can pick and choose. And you can compose a system for your workload. So let's talk about the instances now. So in January of this year, we launched the HPC 6A. It's our first public HPC instance, and this is based on AMD Milan. It has 100 gigabits per second EFA network. This is an instance with 4 gigabytes of memory per core. This is focused on compute performance, lots of cores, 96 physical cores, and we're not doing any simultaneous multi-threading. What we're doing again is we're using the physical cores, giving them to the end user so that they can maximize the resources, using the resources on this instance, and extract the maximum performance for their workloads. So an example of this, we have another CFD example here where we're looking at the airflow across a car when you're designing a car. This particular code was run on almost 40,000 cores. So it shows you the scaling potential of this particular simulation. The dotted line in this graph is ideal, again, as Neil talked about earlier, and the yellow line represents the behavior of this particular simulation. So what we were able to do with HPC 6A is to turn a simulation that was running on 300 cores and took 26 days, which really is, it's not very easy to get a lot done if you have to wait 26 days for something, to something that took 5 hours. So at this almost 40,000 core run, we now are able to turn around a simulation and have results within a workday, which is something that can change things, can change the pace of innovation. It can change the type of things that you're looking for. So what we introduced this week is our next HPC instance, our HPC 6ID. This is an Intel-based instance. Some of our customers like Intel-based instances, some of them like AMD. The Intel instance is a 64-core instance, so it's a little bit lower core count, and it has a lot of memory, and it has local disk. So this particular instance has 16 gigabytes of memory per core, versus the 4, and it has a lot of local disk as well. You'll see up to 15.2 terabytes of local storage. So this particular instance is really good for memory-intensive and data-intensive workloads, things like seismic or reservoir simulations, things like finite element analysis. So I have an example here of some performance that we're seeing with HPC 6ID. This is a code ANSYS Mechanical. It is used for structural engineering. The speed up here, we're comparing the HPC 6ID with a previous similar Intel instance. The R5DN is a Skylake-based instance. It does have a lower core count. It is a 48 core versus the 64 core count. But it has the same network. It has, as the HPC 6A, it has 100 gigabits per second. The HPC 6ID introduced 200 gigabits per second, so it's got a faster network. It's got the more memory and the local disk. And you can see higher is better in this particular example. We're showing you the speed up compared to the two. So the orange is the older Skylake instance, and HPC 6ID is the purplish color. So what about price? So price, performance, or cost is also important. And so this is an example of the cost of doing those runs, comparing again those two instance types. So the HPC instances, the HPC 6ID is also a cost-optimized instance for your HPC workloads. So I want to move on now to the third. We had three particular instances that we have in our HPC family here. This is a Graviton-based, it's a Graviton 3E-based instance that we are pre-announcing at reInvent. This particular instance is 64 physical cores, and it has 128 gigabytes of memory, so it's a little bit lower memory. It's compute intensive, remember again, similar to the HPC 6A. And this one introduces the 200 gigabits per second network with a second generation EFA that has also been announced this week at reInvent. And so this, again, is another choice that users have if they need the higher bandwidth network, they need a higher message rate and a lower latency for the network choice, and they need the strength of compute, and they want to run on Graviton. This is a really optimal choice for that. So the last thing I want to talk about here is we also offer GPUs. I mentioned earlier the top supercomputer that was announced in June of 2022 has both CPUs and GPUs. So we also offer GPUs, and these GPUs are in our P4D instances. They can be used for HPC workloads and supercomputing workloads as well as ML and AI. So this particular type of structure of P4Ds, where we have a collection of P4Ds, allows us to perform very fast operations because we've also made sure that we've collected the instances close to each other, and we have a high-performant network. So the P4D instances is just another option in addition to the HPC instances that we've introduced. So with that, we've talked about the instances, we've talked a little bit about the requirements that users have for supercomputers and how maybe designing your workload to fit your infrastructure is not as optimal as being able to design your infrastructure to match the code you want to run. So let's take a look and bring Neil back and look at how customers are actually using this technology, how they build something using these building blocks and the capability that I described. So, Neil.
Great, thank you. Yeah, I think that's a really good point. We try to start from the beginning. So give an example of the sort of workload and why we even need them as a society to better understand the world around us. Of course, I'm biased. I love CFD. This could be also applicable to weather modeling or energy modeling or financial services. There's so many broad categories that you can use supercomputers for. But I think Heidi actually said the really important thing, which is not having to adapt your workload, which is ultimately the thing that matters for your business or your research, to the compute, but instead to be able to focus on the simulation, focus you want to do, and adapt or bring or customize the infrastructure to meet its needs. So to put this into a little bit more of a practical sense, I wanted to walk through how actually a customer could do this, what it means in practice. And I think one of the key things here is with, I suppose, traditional supercomputers, there has been more of a concept, I suppose, of a single large cluster. With AWS and the way that we have the flexibility and the agility, is you don't have to have that model. Sure, if you want to, like we showed the large simulation of 40,000 cores on a single machine, you can do that. But for a lot of people, they may actually want to have many individual clusters that align to the particular instance they want to use, maybe even operating system, and certainly where they are in the world. So I want to talk an example. So I showed lots of things of cars. So let's imagine that we're a car company, and We can imagine it, but of course we also have customers like Formula One or Joby Aviation or Flying Whales who are doing this day in, day out. But let's just assume we're a car company. And so I start off, so we pick the region that we want to run in, and we have our VPC. And then we use something called parallel cluster. AWS Parallel Cluster allows you to do infrastructure as code, essentially. Through a YAML file, I can specify exactly the cluster I want. I can pick the instances that we talked about before. I can pick the operating system that I want. I can configure the storage I want, all just in a simple YAML file that then I can have version control, I can use GitHub, etc. And it all comes up in a matter of maybe 5-10 minutes. Now, there's, I suppose, two ways I could connect to it via SSH or SSM, or I could actually log on using Nice DCV, which is our remote streaming protocol, so I can actually just have a remote session, so I can visually be interacting with the machine without having to bring the data back. And then I can pick a head node. So this is the thing I log into. And again, I can specify this as large or as small as I need it to be. Of course, as Heidi was saying, one of the key things is the storage side. So I want a high-performance file system, so I'll pick FSX for Lustre. But one of the nice things with Lustre is this integration with S3. So you can actually have a system where you get all the benefits of the durability and the backups of S3, but with the POSIX file system that many people want with FSX for Lustre. But because you can set up things like data repository tasks, it can be automatically syncing between them, so you never need to think about it. In fact, I could make this cluster and then tear it down, and the data's still in S3. And then I could create it again and do it. I can completely test or be more flexible. And of course, then the next thing, which is probably for many the core thing, is being able to set up these different instance types or queues. And I can set up many. It's not the idea that you have to consider of defining this supercomputer 2 years in advance and then waiting for it. You can actually adapt it to your need with many different flexibility and queues. So last week, maybe the configuration of my cluster would look different than this week because we've just launched a new instance. So I can just go into my YAML file, replace that one line that previously said something else to now HPC 6ID, and I can click Update Cluster, and then within 5-10 minutes, I'm ready to start using it. You could not do that with an on-prem system because it would take you months to install this new hardware. The other key thing is the world around us. So let's imagine that this company, like me, lives in rainy Oxford, and I want to have my system in the UK for latency reasons. I want to be able to log on and have a low latency. But then my lucky colleagues who are in sunny California, they want to have their own cluster as well. For latency reasons, they want to be close. So all I do is I go into my YAML file and I just change the region location to be a different one, and I can basically keep everything else pretty much the same. This is really the power of AWS, this idea of redefining supercomputing to be able to adapt the supercomputer to what you need through just a few lines of code and not having to adapt your thing to make it to work. You don't want HPC to be any bottleneck. You should be able to focus on the simulation or the research that you're wanting to do. Now, I could talk about many customers who are doing this, and there's some really great examples, but one I wanted to talk about was Joby Aviation. So just as I was speaking in the beginning about needing that flexibility, they're designing a really innovative eVTOL, electric vertical and takeoff landing vehicle, to revolutionize how people move through environments. I would certainly love to have this sort of vehicle to take me through London or New York instead of having to wait for a taxi or go on the subway. What they found is that by using AWS Parallel Cluster and Amazon EC2 instances, that they actually had the flexibility to run thousands of simulations on hundreds of cores simultaneously. And crucially, that they could use Amazon S3, and in particular with the Glacier function, to never have to be able to delete the data. So they can store hundreds of terabytes of data, and of course, if they need it, they can just bring it back. And what they said to us that actually they found that simulations that would have taken weeks could now happen in a single day. That really is a key difference, as Heidi was alluding to. If you have to wait a week, the most important people in your organization are typically in the context of engineering, the engineers. And so you want to keep them busy and not waiting a week for the results to come back. But I suppose one of the kind of parting things that we wanted to say is that we grow together as a community. One of the key things at Amazon and AWS is the working backwards culture, to listen to customers and to listen to the community on how we can build the things that they want. There is a strong working backwards mentality, but there's also a flywheel effect, which is that by working with these customers and hearing their feedback, that can drive better products that then other customers can use. And then that flywheel continues as we get more feedback from them until we continue to collaborate and grow together as we build better products to try and redefine supercomputing on AWS. And of course, as Andy Jassy has the very famous quote of saying, there's no compression algorithm for experience. And working with customers and building these better things is driving this experience that we have. And we hope that you can enjoy the services and the products that we've launched. So with that, I'd like to thank everybody and to my esteemed colleague Heidi for her contribution to this talk. And if there's any questions, I'd be very happy to take it. So thank you very much.